All right, so this paper is a, well, first interruption. I need power. My apologies. All right, so this is a 2016 paper. I've read later papers, the 2018 papers. I particularly like this paper because of the abundance of ideas that I liked. We'll see why. But the field has been improving. We can talk about the later methods too if you're interested after the talk. All right. Okay. So we're going to talk about abstractive summarization using attentional encoder-decoder RNNs. The main contributions of the model of the paper are going to be modeling keywords. So they're adding this to abstractive summarization, which wasn't there before. They model keywords, explicitly capture syntactic hierarchy. By that I mean both capture the sentence, they have an attention over sentences as well as words. We'll see how it works. Also, they enable the decoder to be able to emit words that have been rare during training or unseen altogether. They still be able to generate those words. We'll see how some of you may guess already. State-of-the-art performance, 2016 August. Creating and benchmarking a new data set for multi-sentence summarization. The data set is called CNN Daily Mail. Was previously used for question answering. Useful data set. They did a bunch of pre-processing and made it available for free to everybody to use for summarization. I do recommend the data set. It's the most challenging data set because it has longer source documents and longer target or summary sentences. So the longer the sequence, the harder the task, right? All right. Okay, so what's abstractive text summarization? So we have extractive and abstractive. Extractive was the technology of the past. It's pretty well polished and used in a lot of places. Basically what it does, it uses a few classic NLP machine learning techniques to look at the source sequence and get rid of things that can be gotten rid of in the source document. Hence, you're going to have a summary that's much shorter than the source, right? It has its own, so it's basically copying over words from the source document to the summary. It has a lot of limitations. Usually what humans do is that they generalize, they understand the idea of the source document, then they rephrase and generate a shorter summary given the salient points in the source document. When I say source, I mean the document that we want to summarize. When I say target, I mean the summary. Okay. Okay, so then why not use just empty machine translation sequence to sequence models? There are differences. So first, in machine translation, you usually have almost equivalent length inputs and outputs. So your translation from your source language usually has the same length in terms of number of words. If we're talking about polysynthetic languages, then we're probably talking about equal number of morphemes that would translate in the almost equal number of words in the target language. Regardless, you have equal length or semi-equal length on both sides. Yeah, and also, so there is a dependency. If the source is longer, usually you want translation to be also longer. That's not the case for summarization. You want to be able actually to output summaries independent of the length of the summary. You want to be able to put half a page summary, 2 sentences summary, 10 characters summary. Okay, so summarization is lossy. You want it to be lossy, and you want to optimally compress the source message. Empty is lossless. You want to keep all the information there. Okay. All right. So they offer 3 main methods, and we're gonna go through them one by one. All of them are gonna use attention. So we start from the simpler model, and we talk about the more somehow more complicated ones. Okay, obviously they use the Bahadano 2014 empty sequence to sequence model, which is basically the attention mechanism. For their encoding, they use a bidirectional GRU, and for the decoder, they use a unidirectional GRU attention. They attend over the source hidden layers, and they use a softmax for the target to generate the target on the target vocab to generate the target sequence, right? Yeah, and in both decoder and encoder, you're gonna have similarly sized hidden states. So there's this trick. So the vocabulary size in summarization and in a lot of other tasks is the main bottleneck, because you get this huge softmax of vocabularies can extend beyond can be from thousands to hundreds of thousands of words. And to overcome that bottleneck, 2014 suggested that you can use the large vocabulary trick, or LVT, from now on the target vocabulary, because that's where the softmax is. We don't have a softmax. We don't generate anything on the encoding side aside from the hidden states. Yeah, and basically the large vocab trick is for your you only build vocabulary for the batch itself. You don't need the words that are in other batches. Use all the source words in that batch because they're all important. You may want to generate any of them during decoding. And you add the highest frequency target words until you reach a cap. And they have a few caps. We're talking about 2K, 4K, things like that. So basically, you'll have all the source words in the batch, plus a few of the high frequency, well, quite a few of the highest frequency target words. All right. Okay, so they have a feature-rich decoder. This is part of their novel approach. It's hard to say it's novel because we've used all of these previously in natural language processing. So natural language processing just recently, like a few years ago, moved from all these to just embeddings and neural networks, right? Regardless, it helps the performance, and need to give it to them. So identifying key concepts and entities using so that's you can use name entity recognition, POS tags, TF-IDF, term frequency versus document frequency, which is used in a lot of places. Search, let's use search, term extraction, and summarization itself. Yeah, search engines I did mention. Embedding dictionary for vocab of each tag type. So basically, what's we're gonna have, you're gonna see a graph where it's where I'm gonna show it more clearly, but what's going to happen is that they have, to mix this with the embeddings of, like the word embeddings, they have a mechanism to bring these scores, TF-IDF, or the NERs and POS tags, all of those to embedding space. And the way they do that is that for each tag or a few of them they call tag vocabulary, they map them to an embedding space, which then can be updated as we go on during the training, right? Similar to word embeddings, which is something I liked actually. Haven't read it elsewhere, but I assume it could have happened elsewhere too. They have an interesting mechanism for TF-IDF, which is a continuous space values. They bin them. They probably did mention, I don't remember the exact numbers how they bin them, but they basically bin them, and those bins then they convert them using one-hot encoding to vectors. Then they concatenate them to the other embeddings. Yeah, so the target is only word embeddings.
So each of those is an embedding. So POS will be one hot encoded vector.
TF-IDFs are going to be one hot encoding, and then everything else is going to be embeddings.
Okay.
Yeah, I got a question. You said the target is only word-based embeddings, but how do you do softmax over the embeddings if it's not a one-hot vector?
You should be able. Why would you not be able to softmax over word embeddings? That's what you do.
Embedding is from 0 to 0. So embedding is like vector.
Sorry, what's 1, 0, and
What do you mean the embedding? How do you describe embedding? Embedding is like a vector.
So yeah, so your softmax, you see the architecture later on, but your softmax layer gets inputs from the hidden state of the encoder, the embeddings of the previous time step, so the output of the previous time step, which is an embedding, right? So okay, so let's say we're at T2 of our generation, right? You'll generate a word, right? It's a softmax, right? That word is then mapped to an embeddings. That embeddings then is input. So when they say they use only embeddings, word-based embeddings, decoding, that's what they mean. Does that make sense?
You mean the decoding part at the input is used for embedding?
Correct.
And basically, you will do the softmax still because you are like a one-hot vector to do softmax.
Well, I don't think you do. So from what I see, so the embeddings map from word to embeddings, right? One hot encoding. You can say one hot encoding, but yeah. Yeah. So just so basically, they're referring, when they say target only word-based embeddings, they're referring to the embeddings of the generated previous time step. So the output of the generated word in the previous time step. So when I say, I don't know, President Obama, and then President, so I want to generate Obama, President is my last generated token in the summary. I bring it to the embedding space by the maps that I have, which is in the target embedding space. Then use that embedding as the output.
Sorry, is this decoder or encoder?
So we're talking about both of them. So most of this is about encoder. Most of this feature is about encoder. It just mentioned that for the decoder, we only use word-based embeddings, not all the other features.
So does each word have a POS tag and NN tag?
Yeah. So in their data set, it is, I think, or if it's not, they like POS taggers, like all of NERs, they're very established in natural language processing. You can just use a tool to tag them. Depending on the data set, some data sets are tagged, some aren't. But if they're not, it's very easy to tag them.
And the embedded dictionary is random, or like a pre-trained
Good question. I think they use in most of the experiments. I may be mixing with other. So in general, there are you can initiate randomly and use other training embeddings. Let me.
I think they use
for the
word-to-vec.
inputs, what they use word to
They
vec.
could have.
They
Okay.
do.
For the inputs was what to vec. So I'm wondering about the POS and
So for POS tagging and ER, for POS tagging, I don't think they use like word embeddings to POS tag. NER, you can use RNNs for NER. I assume they haven't used neural nets for NER. I assume they use like something like older conditional random field. And I assume that the corpora are already tagged because that's not the scope of the talk. They're just using them as features, right? Yeah, but good questions.
I
Yeah.
think that the
These
two
words
of the data sets they use are already tagged with it,
Yeah.
completely tagged.
Okay.
So
Do you remember which one?
I think I mentioned it somewhere
So
in the last.
you're practicing a very good thing. So let me know if you can add. Feel free to add to what I say, or if I say anything inaccurate, feel free. Yeah, I've read a lot of these papers recently. They use different things. Okay, so to take a look at this is the graph I was talking about. Basically, you have all the embeddings. So this is your encoder. You have all the embeddings in TF, IDF, name entity recognition. If some of you aren't familiar with it, it's just it can. So its input is pure text. Its output is places, famous people, named entities, basically. And POS tags is part of speech tags. Is it a verb? Is it a subject? Is it an object? And TF-IDF is some measure of relative frequency that says what is important in the text at hand. And then goes to the encoder. Here's the attention mechanism. The decoder starts getting the last hidden step of the encoder, hidden state of the encoder. And at decoding time, it uses the attention mechanism. This is so far pretty standard attention mechanism. You can use this for machine translation. So each time you want to make a decision on what to generate here, it sees where in the text I should pay attention to, where in the source text.
So what's the output here?
The output here is a summary. Each output is a word in the summary.
And the order is matter.
It's order sensitive, right? Yeah. I assume you found the answer.
Yeah, they use a gigabit corpus and they use some scripts built by the previous authors to generate system-generated tags for
the tags.
pause. Yeah.
Yeah, for the embeddings.
Yeah.
Okay.
For the embeddings,
I think they use word2vec. But
for embeddings, they use word-to-vec for sure.
yeah. Okay.
Yeah.
So they use word2vec. When they say they use word2vec, they train word2vec on the corpus at hand. So each of the corpora, they separately train word2vec on. Okay. Okay, so the other contribution of this work is being able to generate rare or unseen words with respect to training. Yeah, so a lot of times in news, whatever you want to summarize, there are words that they just didn't happen in your training, and your decoder is basically blind to it. So your decoder doesn't have a softmax output that can generate it. The usual way people deal with this is they generate an unknown token, but that doesn't really help the quality of the summary. Like you don't want to have Obama unknown, I don't know, John unknown something. You don't want to have that, right? Better solution, use a pointer network. So pointer networks have been used elsewhere, also in this summary. We'll see in a bit how it works. But just a rough idea, they implement a switch. that decides if I want to generate my summary as before, or I want to have use a pointer that points back to a place, to a position in my source document, and copy that word back to the summary, right? So you don't have, say, Michelle. It reaches Michelle Obama. You use the pointer. You go back, copy Michelle Obama, if it's the right thing to do at that point in time, and it's all learned, nothing deterministic. But we'll get to it briefly. Okay, basically when the switch is on, use generated, otherwise use the pointer. And the switch is sigmoid activation over the entire available context at each time step. And we'll see what that means. All right, so this is the switch. It's a sigmoid activation. You have weight parameters. This is the hidden state of the decoder, I believe. Is the embedding vector of emission from previous time step, as we discussed earlier. And CI is a context vector, so your previous attention, right? You combine them and use sigmoid to get a probability if the switch should be on. Okay, if it's on, it generates. Otherwise, it points. Okay, here's our pointer, the pointer itself. So now I want to point. Where in the source document should I point? What from the source document should I copy, right? So again, if it's not pointing, if it's generating, we all know how it works. It just generates something that it thinks is appropriate. But let's say at this point in time in the summary, it's most appropriate to generate a word from the source document that the vocab of my softmax layer does not have, right? The way to accommodate it is to look back at the document, look at all the weights, and pick the word that is paid most of the attention to, and copy it back to the summary. Okay, so, and the way it works, it's so PAI is a probability of attention at decoding time step I for position J. It's proportional to the exponentiation of, well, that's just parameter vector, parameter Ws of previous time steps hidden value. This is the decoder's time step, and the emission, the embeddings of the previous output, as discussed earlier, as well as the hidden state of the J position in the encoder and a bias. All right. So that's PAI, and to decide now on, okay, which one should I copy, you just use the argmax of this for all the J's in the document.
So
Yeah.
is this like attention?
So it is attention. So it is using the attention. Well, it is the attention over the source, right? It's the same. It's the same thing as you would do without the pointer.
So are we using like the regular backdoor attention model?
As opposed to.
As opposed to this.
Okay, so how is regular and something attentional error?
Like the
different
previous
from-
attention you
Yeah.
mentioned.
Yeah. Oh yeah, okay, so this is, if that answers your question, to use the pointer, to point to the right word to be generated at decoding time step, we're using the exact same attention that's used previously in other words. So previously they just, and also here, at each time step you are using an attention mechanism at decoding time step, right? And this is the exact same mechanism, it's just that you run a softmax over it.
Okay.
And well, you have your rates, right?
So essentially, the previous one tells you whether to the position to look for, and this tells you the exact word to replace from the previous. From the
So,
source.
oh, I see what you mean. And if that's what your question was, so this one tells you how probable is it to switch. So should I actually copy or should I generate?
And once you know you have to generate, once you know you have to copy, this tells
Exactly.
you what to copy.
Exactly. Okay, so this tells you what to copy. And the mechanism is very similar to all the other attention models. And use the softmax just to pick one, right? Because you want to generate.
When it says it just picks one, this comes from like the full set of all words that have been seen in the training. How does like it, where does it, like, is it trying to pick a particular training sample to choose from? Is that a part of the element, or?
So attention in general, the most common attention in sequence-to-sequence models, if you have a source and we have a target, most common attention attends over every word or every item in the sequence of the source, right? So this basically is looking at every word in the source document and saying which one should I copy over here when I'm generating my summary,
Sure.
right? So that's when I say it forces to pick one. That is, we have, I don't know, 100 words in our document that we want to summarize. We want to be able to pick only one word.
Oh, so it pulls one from the input sample, not from the training sample. So it's actually saying find a word from the input.
So this is all in training.
In training, this is
But
training.
this is all in training. But it is, yes, it is from the input sequence
Okay, cool.
during training. Yeah, and when it says argmax, it just picks the index of the item in the input sequence.
Isn't the Rmax specific to the position index? I thought it will, for that position index, it will get a set of words and then it does an Rmax on that. That's not true? Or is it taking it over the entire document?
The argmax is over the entire document, right? ND.
Oh yeah, J and ND. Okay.
Yeah.
I missed that.
Yeah. All right. Okay, so okay. So pointer network optimization. For the pointer network, they use a conditional low likelihood with additional regularization. Basically, they have, so this is during training. They have this G, which they turn to 0 and 1 based on the fact that do they need to copy or do they need to generate, and we know it during training. We know which time at this specific point in time. We know that from the gold standard summaries. We know if we want to generate something that we don't have, right? That's given. So based on that, at that point, if there is a word that's not in our target vocabulary, they're gonna turn it to, let's see, which one turns it generate? I think turns in it into 1 for the generator operator to works. Let's see if I'm right. Yeah.
Yeah, it says in the second bullet point it's equal to
Yeah.
1 for auto vocabulary.
Yeah. For oh, I see. Is an indicator function 1 for out of vocabulary at position I. Okay, so it's 1 if the pointer mechanism has to work.
Yeah.
Right. If something is out of vocabulary, it's 1. All right. And this is this probability of word Y given the previous Y and X, which is your summary input. Sorry, the source document. Yeah. And then factored by the probability of switch, right? am I saying it correct? To this side, yeah. Yeah, so this is the switch, right?
In the second term, the lowercase pi, is that the pointer network there?
PI is, I think, is our PI from
The
last
result
step,
from
yeah.
the previous one.
Yeah,
I
so
think that's
it's our index. It's the probability. Hold on.
That should be this one. This one.
Yes, it's
Yes.
this.
Yes.
So one is not the pointer network, then one is the generator.
Is it so? Okay, let me see.
Because otherwise the second term would be 0.
Yeah, that's what I guessed originally.
Oh yeah, that's because 1 minus GI, right?
Yeah. Yeah. So this was, I think I just wrote this wrong.
So G probably means generator is on.
Yeah, then yeah, that makes sense. So G is generator on, and hold on though, it's 1 minus G, 0, yeah.
Yeah.
Yeah, so then, yeah, okay, the pointer is on when, at this time they use, okay, there's another point. At this time they use, oh, okay, sure. Yeah, okay, so this is deterministic. We're saying, we're assigning G to be 1 or 0 by hand training, but during test time you actually use the switch probability. If the generator's probability is more, as the sigmoid function we see earlier, then it generates. Otherwise, it copies. Okay, yeah, that does make sense. All right, so okay, so this is the pointer illustration. Basically, at any time that you have G, you're generating, and P means that you're pointing, right? So you generate your first token, the second token, your switch says that you need to point, and this is the one that has most of the attention, right? And at each point in time, using the embeddings at the output of the previous time step, as well as the hidden state from the previous step. Okay, this is the other thing, other novelty that I really liked at the paper. I had a similar idea to this, but different enough, significantly different, but it still excites me that they could accomplish it successfully. So hierarchical document structure with hierarchical attention. What this basically does is that it looks at the especially for longer summaries. It can make your task, because your sequence is going to get much larger, right? And again, the larger the sequence, the harder the task for sequence-to-sequence models. What it does, it weights your words based on the sentence that they're in. And when I say words, I'm talking about word embeddings, and when I'm talking about a sentence, I'm talking about the hidden state of the sentence, or sentence embeddings, whatever it is. And we'll see how. So basically, you have an attention mechanism over the sentences. And this SJ is the idea of the sentence, the J position. So you have, I don't know, 10 sentences in your source document. This could be the 5th sentence, right? And this is the attention score for that sentence, the attention score for the word in that sentence is factored by the attention of the sentence, okay? And divided by the same value for all the words and sentences. And I think it adds to one. And I think it's a valid probability. Okay. The other thing that they do is that to their sentence embedding, they concatenate some positional embeddings to the hidden state of the RNN. I think that's actually it's in addition to the sentence embeddings. So basically, each position has an embedding. as discussed before also. And then for those embeddings, they have an attention. It's factored by the word, or better said, the words in the document each is factored by its corresponding attention of the sentence.
So, is both the positions are J? How does it work? If the word is in the sentence, shouldn't the position be relative?
Yeah. So Sj is a function that gets you the ID of the sentence that that word J is in.
Oh, okay. Right.
Good question. Okay. All right. So similar to Sk downstairs, right?
Got it.
Okay. So hierarchical attention mechanism. This is basically everything else almost the same, except for your hierarchical sentence attention. So now you have embedding. So this marks the first sentence, and this marks the second sentence, right? So from the graph, if I'm not mistaken, these two are in the first sentence, and these two seem to be in the second sentence, right? Yeah. So basically, they're only factored by their own sentence. That's all. And then the context vectors are computed now with the new attention model, not just the words, sentence and words. This actually helps in longer sentences.
Yeah. How do you do the sentence separation? Is human doing or just the model?
So there is a full stop, right? Also, there is a full stop if there is a source document that you can do, but also that you can use to separate your sentences. But also, usually in these data sets, sentences are separated by a /t or something.
They have a EOS token also.
Yeah.
Human already done.
Yeah. So that's in the data set. Yeah, that's from the data set. Yeah, it's ground truth. We know it. Yeah. We know where a sentence is separate, but we generate the embeddings, right? All right, results. So GigaWord is one of the most used ones in abstractive summarization. DUC is the oldest one. We'll see in a bit later. But DUC messages are short. I think the DUC was generated from like text messages, old text messages back then. It was a technology. Yeah, I think GigaWord is from Wikipedia. Correct me if I'm wrong. Okay, so this is these are the results. When it says LVT2K, that means 2K is the cap, the LVT trick cap, large vocab trick cap. With when it says one sentence, it only generates one sentence. Yeah, or only reads one sentence. Okay, I'll verify that at the end of the talk. I think it only reads. I think it only reads one sentence. Yeah, so when it says one sentence, it means that it only reads one sentence of the source document to generate the summary. That's pretty short. And LVT2K, similar. It just reads two sentences. 3 uses hierarchical attention. When it says feature LVT2K 2 sentence, it uses all the features that we talked about during the encoding, right? NER, POS tags, so on and so forth. Similar to here, it uses a pointer. We'll see that the pointers significantly outperform others. When it has an asterisk, it means it significantly outperforms. State of the art. Okay. Oh yes, and for summarization, it's a whole different topic on its own, talking about ROUGE scores. But a short summary is that's what we used to evaluate summarization. They're as good as blue scores are for machine translation. What they are basically is how to usually one of the most famous ones are these F1 scores, which is how much of a precision and recall does my summary have with respect to the gold standard.
So it says here it uses only the first sentence in
Yeah.
the one sentence.
Yeah, so it reads during the, yeah, that's correct. Yeah, because the other one wouldn't make sense if used. So traditionally, I think they limit both the summary and the document that they read to a very short size. I think the summary is like something like 75 characters or even less, 75 bytes. So. Regardless, so the other score, so this is F1 score, and you see Rogue 1, Rogue 2, Rogue L. Rogue 1 is when you're looking at each word, when you're computing precision and recall. Most of you are familiar with precision recall, right?
Yeah.
So in a layman term, precision recall is how much of the summary is in the source document, and vice versa would be recall or precision depending on your perspective. And F1 is just the harmonic mean of the two. When it says when it says Rogue 1, it says that it looks at each word in the document and in the summary, and counts that. When it says Rogue 2, it looks at the bigrams. Does this bigram happen in my summary? Does this bigram happen in my source document? And bigrams are just two words that are necessarily adjacent to each other, right? And yeah, and Rogue L, I believe is the longest common subsequence of the two. And it's not necessarily immediate. If the document says Barack Obama said blah 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 something Michel, then in the summary you have Barack Obama Michel adjacent to each other, you still get the score. So the common the largest common subsequence, which is Rogue L, is going to be 3. Okay.
Question.
Yeah.
It's only being trained on 1 or 2 sentences, so it's just taking one sentence and it's generating a summary just off of one sentence?
Yeah.
Yep.
Yeah.
So isn't that kind of a little bit too short to summarize? Like if
It
you're
is.
summarizing a sentence, it's
It is. It depends
pretty
on.
much the sentence itself.
So this
Do you have an example, I guess, of like?
Yeah, we'll see
in the
examples
paper?
later
Okay.
on. But what did you want to say?
so in the paper they mentioned that even though they added more sentences,
Yeah, I
it
just saw
didn't
that.
it didn't change the
Quality of the summary.
quality of the
Okay,
summary.
so there is this hint. It's used all across applied linguistics and NLP, which is for some reason the first sentences and
Yeah,
the
optimal
paragraphs.
position policy.
They have
OPP.
So they have most of the information that the
Yeah.
paragraphs they contain the most important piece of information that the paragraph has. Right? Okay.
It's probably just because how humans write. I think we tend to emphasize a lot during the first sentence,
Yeah.
and it gradually drops. Yes.
Yeah, like I wouldn't start with a stupid irrelevant detail at the beginning.
Exactly,
Of,
yeah.
I'm gonna lose the
Yeah, you're
audience,
gonna
right?
lose your attention.
Yeah, makes sense. Okay, so this ABS plus, let me see if I remember it correctly. So that's an abstractive method. It uses neural machine translation model for summarization, and it uses a bunch of handcrafted features. It uses something else, I don't remember, they use also something else, but handcrafted features, and, oh, yes, the something else is an extractive. So ABS plus is an abstractive plus extractive plus handcrafted features, right? And handcrafted features usually are time and labor intensive, right? Regardless.
Look at that. They have a 91% source copyright. That's pretty bad.
Yeah. So good point actually. So the source copyright is what the authors of the paper came up with, just to see how much of the source document they copy over. Yeah, and 91. It's basically
It's just
it's just a document. It's probably because people, to be safe on the safe side and generate better quality summaries, they sort of rely heavily on extractive methods, and probably that's why it is. All right. I think we covered everything over here. Okay.
Yeah, I got a question.
Yep.
For the decoder part, why do you see there's a need for the indicator? You can use point to network everywhere.
You can do what?
Use point to network. You just point to the source.
Oh, G?
Extract that.
When you say indicator, you mean the G function?
Yeah, basically you don't have to use it, right? So you don't have to
Yes.
use the signal. You just
Yeah.
use the tangent. So you save a lot. Computing time. You don't have to do something.
Okay, good point. If by the indicator, they use indicator to mean G. If by indicator you mean G, it's only during training, right? And it's not computationally intensive. They only set it manually to 1 or 0 depending on is there the need to copy or generate. So G isn't really a function. Well, it is a function, but it isn't really a neural net. It's deterministic given the data. You just want to know. So you want your network to learn when to copy and when to generate, right? Where is the ground truth? How would it know how to do that, right?
I understand that, but why don't you just copy? You don't need to. After G equal 1, you still need to softmax over the word list, right? So you need 5,000, right? And that's a heavy computing cost. So you only use pointer network, and you don't have to remove the G. Just use pointer. Just grab something from the source and put it here.
Right. Okay. Good point. Another good point. So, so the whole reason that we're doing this is to be able to rephrase, right? To generate linguistically sound sentences given some source. More often than not, you want to change the order. More often than not, you're going to change the word itself, right? So if you just keep copying, you're going to run into a lot of grammatical errors, right? If you keep just copying from different places, you're going to run into a lot of.
You still remember the sequence, right? Because your encoder already remember the sequence, encode the sequence. So we'll decode there. So basically, you want to grab the word. Whether the word is a rare word or most rare.
That's the problem. That's the problem because it's not. So a lot of languages don't have just. It's not just words. For a lot of languages, there are morphemes, right? Morphemes are parts of words. Like if you say John, you can't say John have a bicycle. You should say has. Or there are better examples. Like if it's past tense, if your entire sequence is past tense, you can't have a present tense verb, right? You can't say the boys goes, things like that, right? If you keep copying from everywhere in your source document, you're definitely gonna run into. Try it. But promise you, you're gonna run into a lot of grammatical errors.
I think it depends how big your document is, right? If it is if you have many sentences in one document, you may cover that. But if it is a small document, you may need extra words for.
Yeah. Okay. So yeah. So that's one. You reminded me of the other point. So that's one. The other is that you want to be able, if you want to just use the words in the document, you're gonna end up something like extractive summarization, and they have a limit. They can't go. They can't do because if you want to compress more than a glass ceiling, you have to be able to use other words, right? That require smaller syntactic structures, right? You have to use another word to be able to go beyond a glass ceiling. Otherwise, you can just use, not even the pointer, you can just use extractive, which was really effective.
For this algorithm, they have a vocabulary set for the summarization, but they just keep the most frequently used word in summarization. Basically, if your document should be much bigger than your summary. Because if there's a most frequently used word in summary, it's a very high chance that it's also appear in the source. Basically, they should be there. You
So
don't have it, like you should
Not
have
necessarily.
Do we have any examples of generated summaries?
Yeah, we'll see them in the end.
Cool.
We'll see them in the end. So let's let's
I
do
mean, I
that.
know it's purely subjective, but it kind of is.
It's
sort
hard
of
to imagine.
That's kind of the BS test, really. At the end of the day, I mean, like good. I don't know. In my experience, the only really fluid and robust extractive summarization is when you find fiducials by which you can identify summaries written by humans. And you say, oh, you know, person A summarized document B over here. Great, that's a summary. Let's just crib it and plop it. I mean, the promise of this is if it's done right, it'll feel actually like natural language.
Yeah. So that's the promise. We'll see, and it generates. Let's get to that quicker. But I don't think like just a short answer. Maybe we can talk about it offline. I don't think just copying would help. But you may have something else in mind. Let's talk about it offline after the talk. Yeah. So we'll in a couple of slides, we're gonna see the summaries generated. Okay, so this is a DUC. The DUC, as I said, is a smaller corpus. I think a few thousand only examples, and the messages are shorter, bite size. Yeah, this topiary or topiary, however you say it, it's a traditional method. I don't remember. Let me read from it how exactly it works. But it's a classical. Okay, here it is. Okay, okay. So it's a linguistic-based compression and unsupervised topic detection that appends keywords extracted from the article to the compressed output. So some compression based on linguistic insights, as well as unsupervised topic detection, LSA, LDA, what have you. And they were state of the art. Obviously, they compared to them, and they beat this one sentence generation, and that makes sense for the one sentence to beat the previous systems because like they're really short. Do you see text messages are short? All right. And that's the last. So one of their contributions is that they provide the CNN Daily Mail. It's available online. I've used it. It's amazing. It's also harder to summarize this because it's multiple sentences, bigger sentences on the input, bigger sentences in the output. If you want to generate multiple sentence summaries, it's possible, but the problem gets harder because of the longer sequence problem in recurrent neural nets.
What's the longest you've used it for?
The longest that worked or the longest that I used?
Maybe both.
The longest that I've used, I started with 800 input, and I was like, that's this piece of cake. 800 input and 300 output. That didn't work. That produced the 300 times in the output after like days of training. But then we used 2 to 300 input and 50 output, and it works fine. Yeah, and it has the repetition problem. To get over the repetition, to overcome the repetition problem, you need to use either a pointer mechanism or something that remembers the history of the generated sequence.
That's 200 to 300 words per training document for total corpus.
So for your single data point has 300 words of input, and the output of that single data point would be 50 words. And we have the batch size of 8, so 8 of these in one batch.
So just to clarify that, one sentence is doing inference, right? Or is it two?
I think one. So when it says one sentence over, I don't see it anymore.
In the previous line.
Oh, in the previous one. Yeah, I think it's during
inference.
I think during encoding.
During training.
Yeah, during encoding. So you during training. So you only look at the first sentence. Yeah. Well, look, you verified it.
I
Like
verified. I
10 minutes
thought
ago.
it was during inference.
Okay, so you. let's double verify it after the talk. I'm gonna look at it actually. Don't want to misinform people. Okay. Yeah. Okay. So this is they're like obviously they're only publishing their own results. I had more hope for the hierarchical attention. Still, it's not bad, but their bare minimum attention mechanism works best with just the large vocab trick.
So why do we think that is?
They actually mentioned a reason. If I'm not mistaken, they said that the nature of the CNN-DM was more complex. I don't remember. Let me think for a second. Yeah, I'll look at the paper.
Maybe it's just more difficult to train it once you added the additional information in, or it could be overfitting.
This is on a much larger corpus though.
It is much larger. It is much larger. No, I think they mentioned something specific about this corpus. But so we have two things that I'll look up after the talk. This one, I think they mentioned in the conclusion why, at least their understanding as to why. Yeah, I had more hope for the hierarchical attention because I like it, and also the pointer because it doesn't repeat. Also, they're not using their asterisks, so it probably is not significantly different, and they're pretty close, right? But it's consistently better. So.
Oh, it says this corpus comprises multi-sentence summaries.
Yeah.
Probably that's the reason.
Yeah, so it is more complex for one reason that the summaries are longer, right? Yeah, or maybe they didn't actually mention why exactly. But regardless, this is what we were waiting for. So the majority of the summaries produced are good quality summaries, at least so they claim. But for us, they both show the good quality summaries and the bad quality summaries. But it's the overwhelming majority is good quality summaries according to them.
What to S, T, and O?
So S is your source document. T is your target output, is the gold standard you want to compare to, so human generated. And O is the output of your model. So man charged with murder in British backpacker confessed to murder.
Yeah, they're all pretty convincing. I almost like, especially the top one. I feel like the difference between the human one and the automated, I really couldn't tell you which one was written by a human.
Yeah, so it passes the Turing test.
Yeah.
I prefer the automated one because it's shorter.
Yeah, okay. So it suppresses the Turing test. It's gonna conquer us all. Okay, what else? So let's look at the bad quality summaries too. Sorry that it's a little bit too, it was a long list. Let me see if I can, okay, that's better.
So these are not from are these from the paper, or did you run these?
No, they're from the paper.
Okay.
They're not from my experiments.
Okay.
My experiments are worse.
It has an unknown token.
It does, yeah, so it just decides to generate the unknown token. Yeah, so
Isn't
it's
that
not
the gold
determined.
standard though? The T was the gold standard human.
Yeah, it is. So okay, fair enough. Makes sense. So the number is just the number signs are just numbers, right? At tokenization they replace them. Unknown, I'm not sure why would it have happened. It's just something to do with your pre-processing then. It's not the generated output.
Yeah, because the source also contains unknown.
Yeah, yeah. It could be systemic. It could be it could be a name entity recognition or something. Maybe just, I don't know, to be honest. It could be.
Maybe it's just like a really low frequency word.
Yeah, that it would
decided to
never.
take it out.
Yeah. So like that's what I tried to say. So a name entity that's pretty rare, or something that's rare. Yeah. Yeah. Well, broccoli sprouts contain deadly bacteria. Okay. Norway grants
the opposite summary.
Norway grants diplomatic protest to Russia.
there's some truth to it, you know.
I like how understanding you are. Okay, so two of the references that I talked to is the bottleneck is or bottleneck is the attention mechanism, is the person who is responsible for attention mechanism in machine translation, and Sebastian Jo invented the pointer mechanism. All right, thanks very much.